and their combination. So basically what I'm going to talk about is Lagrangian field theory. So namely, as usual, a Lagrangian density integrated over a manifold. This gives you the action functional. And there are classical and quantum problems you want to associate to this. So let me start working. And basically what I will work is on the bulk. So we call this, and space-time we'll call it the bulk. Sometimes I will consider a boundary. And maybe if there is time, we will also consider manifold with corners, but for the moment let's focus here. And first, let me start with the bulk. And for simplicity, let me assume that it has no boundary. And also let me start with the classical problem. So the classical problem, as you know, is looks for the critical point of this action functional. So if there is no boundary, there are no boundary conditions. If this boundary is not empty, then one problem is what are boundary conditions. There is one of the things you have, of course, you've seen it, several examples, somehow pointed like what is the general structure of boundary conditions. If there are symmetries, and by these now I mean gauge symmetries, what you are interested in actually the space of critical points modulo the gauge symmetries. And these may be singular, both just taking the zero locus may be singular and further dividing by symmetry may be even more singular. So one thing that you might want to do is to go to some cohomological resolution of the space. So I will explain this in detail, but this means essentially that instead of considering this set, or space if it's additional structure, you are going to consider some chain complex, typically with some additional algebraic structure, such that its cohomology, well in the ideal case, its cohomology is concentrated in degree 0, and its cohomology in degree 0 gives you something that describes this quotient, for example, the algebra of functions on this quotient. And the idea that really you move to the different category, you start with some category of sets or spaces with properties and so on, and you move just to the category of chain complexes of special algebraic objects, and you just consider morphism in that category, and typically you don't want to go to the cohomology because basically you go back to this situation. So in this setting, this is called the BV formalism. I mean, BV formalism was not developed for this, but it turns out to be useful also for this, and I would say this is somehow the classical BV formalism. Okay, and well, in modern, people doing now in algebraic geometry, this is related to what is called now -1 shifted right symplectic geometry. Okay, then there is a quantum problem associated to this, which is, roughly speaking, trying to make sense of the integral over some space of the space of fields of the exponential of the action function. What I'm going to consider is the perturbative definition of this, which means that you look for the critical points, you span around them, you hope that the Hessian is non-degenerate. If this is the case, then you somehow define this as just like the expansion of the non-quadratic terms, and you use just the Bublik Gaussian measure to compute that. And then you go down to Feynman diagrams and blah, blah, blah. And then the usual problems that sometimes the Feynman diagrams do not converge, so you have to go through regularization, renormalization, and so on. I will not go into that part, but that's about the whole thing you want to do. Now, again, if you have gauge symmetries, there is a problem in this approach because the critical points are not degenerate, so the Hessian is degenerate, so you cannot even start the Gaussian expansion. So to do this, you have to get rid of the gauge symmetries, So one way would be just, well, instead of working on the space of fields, you'd work on the space of field modulo of the gauge symmetries, but this, okay, it's not very nice because it becomes some singular space, certainly not affine. So this is very problematic. So there are some ways around it where they got developed by Fadel Popov and then generalized by DRST, and somehow in its full glory by BV, the same Batan Wilkovitsky as here. And so this is a method that somehow tells you how to deal with gauge fixing in a consistent way, in the sense that you, well, instead of taking the quotient, you take a section of what this quotient would be, and you put a gauge fixing, you make your, now everything becomes not degenerate, you can make your Feynman diagram expansion, and then the question whether this is, well, reasonable in the sense that, well, the final result, physical result, should not depend on the choice of gauge fixing. So the theory we want to prove is that your results are independent of the gauge fixing. So what you can do with these techniques, for the levels of generalization, is to show that the result is invariant under deformations of gauge fixing. Invariance under deformations of gauge fixing. The best you can do. Okay, so this is BV, and well, I will call this actually now the quantum BV. So it's related to this in somehow the classical version. There's some missing ingredient in the classical part that you have to add in the quantum version. Okay, the other thing that I want to talk about, and actually we'll talk about it before doing this, is what happens if you have a boundary. So if the boundary of the manifold is not empty, then, of course, there is a problem that you have imposed boundary conditions in a reasonable way. Reasonable, okay, first, for a point of view of PDE, you want the problem to be well posed. You want to be sure that, well, you have, well, best possible case, you have unique solutions, otherwise some discrete set of solutions, some space of solution you can understand. And the other point is what to do if you also have gauge symmetries, which is related to the fact that your Lagrangian density is degenerate. Okay. So here, one idea is to look for a special case. So you take your manifold to be of the form some, well, manifold of dimension lower by 1 across an interval. So actually, locally, near every boundary component, your manifold looks like this. So this is the first case you have to study, and typically it's enough to study this case. So in this case, the boundary consists of two copies of the sigma. Well, if you have an orientation, this will be one of the two copies of the opposite orientation with respect to the other. And then, okay, you want to study what are the possible boundary conditions, but in this setting, you can also interpret this interval as time. And so there is a related problem, which actually is very closely related, which is an initial value problem. So I will focus on this, but then it's about understanding initial value problem also enough to understand the general problem. So initial value problem means that okay, you write down your PDEs, I mean the other Lagrange equation, the critical points, as somehow just focus on the time dependence and on the partial derivative sum operator on some infinite dimensional space, and you want just to specify initial condition let the system evolve. Now, as you know, in the typical non-degenerate case, there is a space of Cauchy data, right, the possible initial condition, which let me call it by M sigma, which actually turns out to have the structure of a symplectic manifold. Time evolution is just the Hamiltonian flow of some Hamiltonian function. Okay. Now, from this point of view, the quantization is conceptually obvious, a little bit very complicated. So quantization means that you replace your symplectic manifold M sigma by some Hilbert space, and you replace the Hamiltonian function by some self-adjoint operator. And then you let it simplify. Of course, this is not easy in general, but somehow this is what you want to do. Now, the question is, what happens if, so the problem is what happens if the Lagrangian density is degenerate. So, well, not details, but essentially degenerate means that, for example, if you try to do the Legendre transform to go to the canonical version of the phase space, there are problems. And or these are related to the fact that there are gauge symmetries. And so in this case, right, this picture does not work on the nose. There's a problem basically that, not ever possible, field configuration you give in sigma could be extended to a solution. So you have to take something less. So essentially what you can do in this setting is, first of all, you can associate to the boundary some reference symplectic manifold. Maybe let me do it here. So these are what we call boundary fields. And inside this symplectic manifold, there will be some subset, often a submanifold, which are the allowed initial conditions. Typically, this is what is called a coisotropic submanifold. We'll tell you more what it means if you don't know it. But in particular, this submanifold typically is not symplectic. I mean, in the non-degenerate case, this submanifold is the whole f of sigma, so it is symplectic. But typically, this is no longer symplectic. So you cannot formulate this program. But what you have to do is to do some symplectic reduction, which basically you quotient out by the degeneracy of the would-be symplectic form, which means there's the restriction of symplectic form from here to here, and then if the quotient exists, is nice and so on, this now is a good symplectic manifold, and this is called the reduced phase space. So that the usual terminology for this symplectic manifold initial data in the non-degenerate case is the phase space of the theory. In mechanics, it's just a cotangent bundle, right, of configuration space. And well, in this degenerate setting, you have to go through this procedure. You have this correct notion of a reduced phase space, and now you formulate the evolution here. Okay, so here you can also construct the Newtonian function and then try to quantize. The problem that, of course, this might be also quite singular. Typically, it is very singular. So again, you don't want to do that, and so you do again some homological resolution of this, this symplectic quotient. So first this subset and then the quotient. And in this case, the homological resolution goes under the name of BFV, Bataillon, Fratkin, and Wilkowicki. So the same BV as in BV, but in addition also Fratkin. And so again, this is a homological resolution. So you have some chain complex with some algebraic structure, because at the end you want to describe, right, some symplectic manifold. Dually, you work with the algebra, so you have a Poisson bracket. So there will be some chain complex of Poisson algebras, graded Poisson algebras with certain properties, and somehow this is somehow the correct version. And then the idea is that now you can try to quantize this. So the quantization should no longer be just some Hilbert space, but some, now will be some, the Hilbert space itself will be some chain complex, and the physical Hilbert space should arise as a zero homology of this chain complex. Okay, so this is the procedure you want to perform if you're lucky and everything works. Okay, so this is for the initial value problem. And what about the boundary problem? So for the boundary problem, well, what you know for mechanics, and we'll explain why it works in general, is that suppose you are in this nice non-degenerate situation where you have some symplectic manifold, the phase space, associated to a boundary components, then the boundary conditions are the choice of a Lagrangian submanifold in this symplectic manifold. For example, if you just take mechanics, the usual phase space, coordinates are positions and momenta, typically you fix the positions, right? Now we have to take a boundary problem, so like initial time and final time, so if you're in this situation as a boundary, and typically you fix positions at the beginning, positions at the end, just selecting the position inside the usual phase space is the Lagrangian submanifold. Okay, but this was more generally. You can take more general Lagrangian submanifolds. Now, if you go to the degenerate case, you should choose a Lagrangian submanifold of this reduction, which is of course with singular. And well, what to actually do is to choose a correct, the Lagrangian submanifold in this setting in the appropriate way. Okay, so this is somehow the idea. And then let me come to the bulk to boundary. So now we have a manifold with boundary. So now, well, okay, I'll start talking about it here. So what happens is that, well, you have to choose a Lagrangian submanifold to make sense of boundary condition, but actually, with the boundary conditions to be such that you don't get boundary terms when you take the variation of the action. Okay? So we have delta S, no boundary. This is the classical picture, which you can extend here. And essentially, from this well, derived point of view, what happens is that somehow the Euler-Lagrange equation can be interpreted as giving some Lagrangian structure in here. It's somehow the generalization of what a Lagrangian submanifold is. Then you have a second Lagrangian structure that you choose, and you do the derived intersections. So now the solutions, the space, moduli space of solution, in this settings becomes the derived intersection of well, the Lagrangian structure given naturally by the Euler-Lagrange equation and the given Lagrangian structure that you choose a boundary condition. Yes?
For example, this M ipsil can be the derived character stack.
Yeah, that's, yeah, you have to derive, yeah, sure. Yeah. Okay. And so this for the classical part, and then there is the quantum part. So in the quantum part, what you want to do is to do right, this functional integral over the space of fields, but with boundary conditions. And so the result will be a function of the given boundary condition. So if you think of, yes?
I wanted to ask the space H after quantization.
This one?
Yes.
Yeah.
Before taking the zero homology, is it a Hilbert space?
No, not really. No. I mean, actually, also behind after that. Okay, first, if you want to make it to a space of two or more, I will not do it. The thing you can construct naturally is some filter in a product. And you should complete it to make a Hilbert space. Here on the graded version, this is also a bit more complicated. But the point that, like in cohomology, you should be able to complete it.
That H is derived scheme module.
Yeah. This H. Which H? No.
Oh, that
Yeah,
H is derived scheme module.
Yeah. Okay, so then the idea that now if you do the functional integral with boundary condition, you have to fix a boundary condition to make it in an appropriate way. So the result will depend on, well, on the gauge fixing and on the boundary conditions. Somehow you want to check that everything is variant under deformations of the gauge fixing, but you still have the dependency on the boundary condition. This is there if you just think of mechanics, right? In classical mechanics, you fix say, for example, the Lagrangian submanifold to be just spanned by coordinates. So you fix a position coordinate, and the result of this will give you the wave function depending on the coordinates as a function of the coordinates. Okay, so then when you go to the degenerate case, what you should see that the result of this approach should give you some element of this graded space, some element in degree 0. which should be closed under the differential you have on this chain complex. And moreover, you have to make sure that when you deform the gauge fixing, this psi changes by an exact term, so it defines an element in cohomology. Some class 0, so this becomes the correct state associated to this. Again, here I'm cheating a little bit. This is really not a Hilbert space. For example, if you think of that situation, this is what I call psi, I call the wave function. Actually, in that example of a cylinder would be the evolution operator, which is not, of course, an element of the tensor product of the Hilbert spaces associated to the two surfaces. So here I'm really not working. I mean, I'm somehow enlarging the Hilbert space to allow it also for this operator. I mean, the evolution operator is not a Hilbert-Schmidt operator. So working a bit easier. Okay, so now the machinery to make sense of this is what we call the BFV. Is something that puts together the BV construction you have in the bulk with the BFV construction you do on the boundary in an appropriate way that allows you both to understand this derived intersection and this procedure for quantization. Okay, so this was just an overview. Now we'll go into details. So, okay, so if you no question, I will move to the classical part. So, everything. Okay, so what I'm going to describe is essentially what was developed by Kioskin to Chiev. We somehow expanded it a bit. I will just write K and T because I'm not able to write Kioskin to Chiev without making mistakes. And so the starting point is a Lagrangian field theory. So as I said, essentially you write the action functional associated to some space-time manifold as the integral over space-time of a Lagrangian density. And so this is supposed to be, say, functional on, we'll not say what infinity means, but somehow a functional on the space of fields. So there is some space of fields which consists of local data. So think of these, for example, functions, just taking for the scalar fields, connections, if you're taking the gauge theories, so space connections, or sometimes can be maps from the manifold N to some fixed target manifold. If you want to do sigma models, could be a section of some vector bundle, for example, spinors, and so on. Okay, so but these are just local data. So essentially, this is a space of sheaves. And the Lagrangian density is local in the sense that it just depends on finitely many jets of the fields at each point. It produces a density that you can integrate over the manifold. Okay? So, I mean, also no mathematician, just let me give you examples. So if you do the scalar field, so the space of fields are infinity functions on the manifold M, and the Lagrangian density is just like G mu nu, d mu phi, d mu phi over 2. Well, this is some fixed pseudo-Riemannian metric on M, so this is some data you might have, and maybe you want that also potential, which just depends on the field itself with no derivatives. Another example is, say, Yang-Mills theory. So in this case, Fm is a space of connections for some principal bundle, and the Lagrangian is 1/2. Well, you should put some coupling constant here, but then you just take the curvature of A, wedge product, the Hodge dual of the curvature of A, so you need the notion of Hodge dual, and so on. Okay? So these are, let me stop with the example, maybe just let me do this stupid example, which is mechanics. So in this case, well, the manifold is necessarily, well, either R or some interval, and so the space of fields are maps now from M to some other manifold N, for example, Rn. And so we call this map Q, and the Lagrangian is 1/2 Q dot norm square. So you need some Riemannian metric on the target to define what the norm square is. Okay? And again, you can subtract some potential. Now, notice these will be two examples of non-degenerate theories, and this will be an example of a degenerate theory. Okay, okay, so now, okay, what I want to tell you is what structure does this space has. So, for example, in this example, okay, you can do some functional analysis, some infinite dimensional vector space. You can put some topology also here. So one way, if you want to go more in details, is to think of the space of fields some infinite dimensional manifold, some topology. For what I want to do is better to take a Frechet topology, because I mean I really want to work with infinity fields, especially when you do have a gauge theories, right? Well, whenever you do gauge transformation, you introduce some derivatives. So you want to specify the derivatives. So it's better to think of this as a Frechet manifold. There are other ways of dealing with this. There is a more categorical way where you really think of these somehow generalized manifolds. You extend the category manifold to sheaves over the category manifolds. Or there is other way, which is the variational complex. You really work with the infinite giant bundle and understand this in that sense. So, but I don't want to go into details. The only thing that you should think of the action function as a function on the space of field, and the functional derivative of the action functional as a one form on the space of field. Okay. Now, okay. Now, what happens is by the structure here is that like there are some derivatives of the fields. So when you take this differential here, you will get well sometimes you will get the variation of the derivative of here, or the derivative of variation. So you don't want to have that. So you want somehow to integrate by parts and isolate the terms that do not contain derivatives of variations. So, no derivatives of variations. And then you have some other part where, well, which appears when you integrate by parts to get rid of all the derivatives. Okay, so let me maybe explain this in example. So let's start from last one, in the case of mechanics. Right, you take the variation, like, let me do it in the case where the target is just R, for simplicity. You have to take the variation of 1/2 Q dot square to the mass to be more physical. So this is like M Q dot times delta Q dot, right? So this is what you don't want to have. So you integrate by parts, so some interval, right? So if you integrate by parts, you get minus M Q double dot delta Q, and then you have a boundary term, which in this case is just evaluation at the endpoint. Now let me write it as integral over the boundary. So this just means evaluation at say the interval, say this interval AB. It just means evaluation at B minus evaluation at A, as usual, and over the boundary you have the term M Q dot delta Q. Okay, so this is the usual computation you do. And now, okay, already in this example, what you see that here you see the Euler-Lagrange equations. This set the potential to 0, so this is just the usual Newton's equation without potential. So these are the Euler-Lagrange equations, so this is why I call this term small el. This whole term here, my el. And then there is, well, this boundary term, which is what I would call alpha, okay, which in this example just consists of the one form mass times velocity times differential of position, both at the final point and the initial point. Okay? And so, and well, if you think a moment, well, what is mass times velocity times differential of position? Well, this is sometimes called the Noether one form. And important point that if you take the differential of the Noether one form, that we call it omega, you get m dv dq, which, well, if you remember the usual setting, momentum equal to mass times velocity is dp dq, which is the standard symplectic form on R2. Okay, so this is what like gives rise to this Hamiltonian interpretation of the evolution equation. Okay? So the idea now is to generalize this. So just take this, right, as a definition. So it's this side as a definition. You take the variation of your fields, integrate by parts. So we have one term where there are no variations of derivatives of the fields, and this will contain the Euler-Lagrange equations, and there is some boundary term, okay, which you can think. So by construction, both ELM and alpha m have to be viewed as one forms on the space of fields. So now you can do the exercise for this other theory and see what ELM and alpha m are. Okay. Now the next thing is, well, you can consider the zero locus of this one form here. The points on the space of fields where all the components of the one form vanish. So for this example, will be paths that satisfy the equation m double not equal to 0, okay, with no boundary conditions. And we call this the Euler-Lagrange locus, so we call this capital ELM. Okay? So these are essentially solutions to Euler-Lagrange equations, but no matter what boundary condition imposed. Actually, there are no boundary conditions. So this space is not, to say, a unique solution. It's some complicated space, typically still infinite dimensional. Okay. So now there are some, you should think of this as a submanifold of the whole space of fields. So for this inclusion, yeah. Okay. So sometimes it is really a submanifold, sometimes it's a bit singular, but that for the moment, to simplify notation, let's assume that this is a submanifold. And then there are some immediate remarks you can do. The first remark is that if you restrict the one form alpha to this submanifold, right, as you see here, when you restrict alpha to the submanifold, well, this restriction becomes 0. So the restriction of alpha to the submanifold becomes the restriction of the variation of the action. Right? So this means that the restriction of alpha to the submanifold is exact. Okay. The second observation is that if you change the action, so if you deform your action by some boundary term, so this means that this would be an integral over the boundary of some density depending on the fields defined on the boundary. This is something that like you wouldn't see if you're like you started on the field theory without boundary, but if you have a boundary, you can change like your action by something that appears on the boundary. This will not change the Euler-Lagrange equation. So because when you do now the construction, right, when you do now delta S twiddle m, you want basically you will get something like this. Essentially, I mean this term here is already on the boundary, so it will not affect this part here. The only thing that will change is the one form, and essentially we'll see that the new one form is related to the old one just by the variation of this boundary contribution. Okay? So this tells you that if you perform this operation, which somehow at this level physically should be a bit irrelevant in the sense that it doesn't change the Euler-Lagrange equation, you're changing this neuter one form by an exact term. Okay, so that means that the correct thing is to work with alpha m modulo exact terms. And one obvious way to somehow get rid of the exact terms is to consider the variation of alpha m, which we will call omega m. And so this is now invariant under these operations. Okay, so now this is a two form on the space of fields. It's closed because it is exact, and is invariant under changing the boundary terms in the action. So this is a bit more physical. And then, one immediate consequence is that now if you restrict this omega m to the Euler-Lagrange locus, since alpha there becomes exact, delta alpha becomes 0. So it vanishes there. So whenever you have a two form, a submanifold on which the two form restrict to 0, it's called isotropic. So this can say that the Euler-Lagrange locus is an isotropic submanifold with respect to these two forms. Okay. Now, the idea is now we want to do some symplectic geometry. Well, why? Well, because, you know that eventually you would like to explain time evolution in terms of symplectic geometry at the classical level and do some quantization quantum level, so you have to do something symplectic. And the data here is that you're almost there. You have a closed two form, right? The only problem that this two form is degenerate. So what you want to do is to take now the quotient of the space of fields by the kernel of these two forms. So the kernel of these two forms consists of all vector fields. They kill the two form by contraction. So this kernel consists of vector fields on Fm such that the contraction with the two form is 0. Okay? So assuming that this quotient is a smooth manifold, right? And so then we'll have a projection over here. Then there will be a unique two form on the space, right? Such that this pullback is the original two form. Because this is the projection to the quotient is subjective submersion, right? So why is this true? Well, first observation is that what immediately this implies that also the Lie derivative of omega with respect to such a vector field is 0 because omega is closed. So this is important. So this is delta omega plus delta omega. So this is 0 because the two form is closed, and this is 0 by this condition. So you automatically have that the form is also invariant. So if you have a form which is at the same time horizontal and invariant, it's necessary to of form of quotient. And this form is unique because it's subjective submersion. And moreover, this is now non-degenerate because you're precisely quotiented out by all the vector fields that they were in the corner. So this is symplectic. So this tells you that if you can do all these operations, there is a natural symplectic manifold you can associate to your field theory on a manifold and with boundary. Okay. So as we will see in a moment, actually I can already tell you, is that, well, since this alpha m, right, so actually it turns out that alpha m is necessarily of the form something integrated over the boundary, because basically the way we obtain it is by integration by parts. So this shows you that, well, when you do the omega m, will be something, well, okay, it will be something, the delta inside, cheating a little bit, but essentially you see that the two-form omega m, right, only sees the boundary of m, which means that vector fields on the space of fields, the change the field in the bulk, but not right, in the neighborhood of the boundary, are certainly in the kernel. Which means that this quotient space essentially only depends on the boundary. So we'll use this notation, f boundary for the boundary of M, to stress that this really only depends on the boundary of the manifold. Okay? In terms of the field, you have to be careful what does it mean. So when you write down this thing here, what still appears here, well, here we'll see the fields, for example, evaluated on the boundary, but you can see still derivatives of the fields evaluated on the boundary. So, for example, already in that example, right? But you can also see transversal derivatives of the fields, the velocity. So this means that essentially in this quotient, which I call like the partial, f partial associated to partial m, here essentially you will see, well, fields plus some transversal derivatives, maybe plus extra stuffs, and so on. But essentially this is what you're going to see. So for example, in this example, right, when you consider this form mq dot delta q as a one form on the whole space of fields, you see that there is a huge kernel. Because, for example, well, this sees only the velocity, well, so it sees the position and the velocity of, say, your particle at initial time, but doesn't see the acceleration. Okay? And doesn't see the third derivative and so on. So when you think of it on the space of field, this is a huge kernel. When you do the quotient, basically you kill everything, and you are just left with the information of position and derivative. So in this example, right, f boundary, and let me just associate it to say one of the 2 points. I mean, you can do the same construction of the other 2 points. Right? This is the space, right, of q coordinates and v coordinates, right? And this is what you understand at q dot. This is the only thing that is left. Okay? And this is a non-degenerate symplectic form, which is the mass times the velocity, dq. Okay? So this is the result of that procedure in this way. Right? So you think of mq dot delta q evaluated at the boundary points as a one form on the whole space of fields. So its differential is certainly, as a two form is certainly degenerate, but when you mod out by the whole kernels, you are just left with the usual phase space and the usual symplectic form. The result of this operation. So one thing you have to stress that if you follow this procedure, even in the non-degenerate case, for example, mechanics, you start with something which is degenerate, actually very, very degenerate, and you have to do a first reduction to get a symplectic manifold of fields associated to the boundary. Okay? So from this point of view, there is still no difference between degenerate Lagrangian and non-degenerate Lagrangian. Okay? So now we're going to see what happens, for example, what's the difference between, say, mechanics and, I don't know.
Can I ask a question?
Yeah.
I'm a bit confused about this construction. Suppose we take a different M to be, let's say, different surface
Yes.
with the same boundary but different number of genus.
Yes.
Are you basically saying that the F constructing this way doesn't depend on the number of genus?
This does because this does because like this construction only sees this one form, and this one form only sees what happens on the boundary.
Okay.
I mean, the space of solution will be different. The information on the bulk, for example, different genus, will appear in what I'm going to tell you next. This part is completely independent of the bulk. Yeah. Okay, so okay, now for simplicity, let me assume that this construction works, and fortunately, in, well, the most physical example, it works. This quotient really makes sense as a smooth infinite-dimensional manifold. Well, in this case, becomes finite dimensional. In general, it will still be infinite dimensional. So this part works. One nice thing you would like to have is somehow you would like to make sure that also this one form is basic. So let me make an assumption. There is one form alpha boundary on this Gaussian space such that the original alpha m is a pullback. Okay, so this is not guaranteed. You know that the two form is basic, but the one form is not necessarily basic. So this is not guaranteed. Fortunately, it works in several interesting examples. And if you have this, then, well, there are certain properties. So first of all, this alpha boundary M is unique. Well, again, just because the projection is a surjective submersion. The symplectic form is now exact. And the third property is that the variation of the action now can be written as well, Euler-Lagrange one form plus the pullback of this one form. Okay, so you get these interesting properties. Now, this is an assumption, as I told you. It's not guaranteed to work. I can tell you that in several examples it works. Several physical examples it works, so it's interesting. There are some examples where it does not work, but, well, it almost works. At least it works locally. So in examples, this works, well, at least locally. By locally it means that, well, you're working with differential forms and the RAM, so you want to somehow to write this close to form as an exact one, and this works locally, so in the sense that you should think of alpha m and alpha partial m as connection one forms for some line bundle. Okay, so you no longer require these to be globally well defined. So alpha itself is not globally well defined as a one form, but it's a connection one form. Still, this is not guaranteed. This might also fail, but in basically in all physical examples, at least in this version, it works. Okay. Now, this interpretation of alpha as a connection one form is actually consistent with this operation here. Say that remember that alpha was defined up to the differential of a function, which is the way you can change the action by boundary terms, and correctly you should think of this as some gauge transformation. Okay. Now at this level you think of this as like alpha m as a connection one form on a trivial line bundle. And this just gets transformation in that case. And only when you go to the quotient, it might happen that you really have to consider this as a connection form for some non-trivial line bundle. But actually, if you think already in view of quantization, what we are doing, really, you should consider the exponential of the action. And well, and this transformation tells you that this changes by the exponential of this phase. So you really think that, well, actually there is some line bundle behind, and this shift of the action is really a gauge transformation for section of the line bundle, and so this becomes a correct gauge transformation for the connection one form. And you don't have to impose this line bundle to be non-trivial. Actually, there are interesting examples of field theories where, well, these are only local, which means that you have a non-trivial line bundle. Just to mention, the simplest example you can think of is a mechanics, just a particle, coupled to some fixed background magnetic field. And the point that when you write down the Lagrangian, you have to introduce the vector potential. You cannot write it direct in terms of the magnetic fields, which makes the Lagrangian defined only locally. So what makes sense is really, well, to mechanics we say, well, the action is defined up to total derivatives. In this language, it means that like the action is well defined. Well, actually, the exponential, but the action is well defined as a section of some line bundle. This transformation now becomes a Gauss transformation of that line bundle, and this one form, even already before taking the quotient, is really a connection one form for the line bundle, not a global one form. And another example, which is about the generalization of a sharp particle magnetic field, is the Weston-Witten theory, where we have the same phenomenon. That's Weston-Witten theory. You, in principle, have some closed free form to define the theory, but when you write down Lagrangian, you choose locally a two-form whose differential is a given closed free form, and then you see this phenomenon. Okay. Let me see. I don't know. Yeah, I started a bit late, but you're blind, so what should I do? Continue 5 minutes, or?
I think when is a good place to stop? So if you need 5 minutes for that, that's great. But if now's the time.
I think it's probably a good. I mean, this would take. I don't know if it can take 5 minutes. Is it okay? Okay. We could finish this part. Yeah. Okay. Just take. Yeah. Okay. It's better to stop in 5 minutes. I can say a bit more. Okay, so okay, so one thing now you can consider, like, related to your questions. How do you see the bulk from here? So what you see now is that well, we have our space of fields, and on the one hand we have well, the inclusion of the Euler-Lagrange locus, and on the other hand we have the projection to this space symplectic manifold boundary fields. Okay? So what you can do, you can take the composition of the two, we call it M. So these are essentially, well, physically what it means here. So here, points here are solutions to the Euler-Lagrange equations without imposing the boundary conditions. And well, this is the space of boundary conditions. So what you get here in little m, these are the boundary fields that corresponds to solution of the Euler-Lagrange equation. So these are, so this is the sum of the set of boundary values of solutions. Okay. As, right? Well, okay, ideally a submanifold of this symplectic manifold. Okay. Now, if you think of mechanics, for example, take without potential, right? The Euler-Lagrange equations, I say the second derivative is 0. So, okay, so what is a solution is some straight line. So what happens here, this space here, let me give an example in mechanics, right? This quotient consists of two copies of the tangent bundle of R, right? Right, so here we have position and momentum, position and momentum, again, say initial position, initial momentum, final position, final momentum. Okay. And if you think of a solution, in this case, the momentum does not change, the velocity is constant, whereas the position is translated by the momentum. So the L here, in this case, becomes something like, well, there is initial P, which and equal to the final P, there is the initial Q, and the final Q. So suppose that the interval is 0 to T, so the final Q is T times P plus Q. Okay, so you get these submanifolds. Now, if you think a moment, this space is 4-dimensional, this submanifold is 2-dimensional, it's just parameterized by P and Q. And, well, this simple exercise, if you think of the symplectic form here, to be d2f, d2f minus d2i, d2i, and there is this minus sign because, like, when you evaluate the evaluation of the integral, this is a minus sign, the opposite orientation of the endpoints. So it turns out that if you restrict the two form over here, it's 0, so this is isotropic. So this submanifold is isotropic of half dimension, so this is what is called a Lagrangian submanifold. Okay. So now I didn't impose boundary conditions, but what naturally have is some Lagrangian submanifold of the symplectic space of boundary fields. So this is what the bulk gives you. Now, this was a specific example. Well, what happens in general, well, one thing that immediately happens is that this LM is isotropic. And, well, you have it because, well, this ELM was isotropic, so when you do this construction, you see that it is isotropic. Another way to see that, well, if you really can do these things locally, I mean, in the image, right, when you go, you want to see what happens to this one form, where in the image of this map, this disappears. So this means that locally this one form is exact. So certainly its differential is 0. So the two forms vanish here. So this is the general thing that happens, that this construction, say, to field theory, okay, up to singularity, naturally associate a symplectic manifold associated to the boundary, and an isotropic submanifold of this symplectic manifold. So these are the data of the field. And somehow the idea that you should think of this as some sort of categorical data, in the sense that now you can rephrase field theory. Somehow you're given field theory as some sort of a functor, right, from the category of space-time manifolds, which means manifold of the given dimension and the given structure you need to define, to some other category. Well, what is this category? Well, the objects here should be symplectic manifolds, possibly infinite dimensional, and the morphisms should be these sort of things here. So somehow, so a morphism from, say, one manifold, F1 to F2 should be thought of as an isotropic submanifold of F1 cross F2, where, well, you have to change the sign of the symplectic form, like in this example, 1 or 2 copies. Well, why do you expect this? Well, the question is, well, what is the composition? So the composition is, like, let me just go here. So suppose that you have your manifold M, which is built, for example, by gluing together M1 and M2 along the common boundary sigma. Now think a moment, what is the other Lagrange? So I suppose, for simplicity, I mean, there could be other boundary components, but let's ignore them. So what is the space of solution to the other Lagrange equation on M? Well, what you can think is that, okay, you have once you have a solution, you can restrict the solution to the 2 copies. In particular, you can get a solution on M1 and M2. And, well, the properties is that not every pair of solution on M1 and M2 corresponds to a solution on the whole M. What is important that they have to match here. Okay? And so, essentially, if you think a moment also the way this space was defined, this is essentially actually, okay. Essentially, you see that the space of solution on the whole M is given by pair of solution and M1 and M2, such that their boundary values in that sense. It's a fiber product over like the space of boundary fields associated to sigma. So, well, this is actually the you can think of. Okay, now, okay, if you want to go categorically, think of M being something like the go sigma interval. So this is your M, and in this sense, ELM is a submanifold of F sigma. Okay. When you go now to LM, this is some manifold of L sigma, F sigma boundary cross F sigma boundary, and this isotropic there. And so here you start thinking of this as a morphism, and this composition tells you that now if I extend this by something else, I have to do this operation, which well, turns out to be the composition of relations. So just let me use this standard set theoretic language. A submanifold of a Cartesian product is a relation, and the composition of relation is a relation that you get by matching the intermediate points, which is precisely what you get out of this description. So here should be actually isotropic relations, and the composition of relations. Let me just explain what are the problems here. First, this is not really a category. The composition of submanifold, the relation is not a submanifold. So this is not really a category. But on the other hand, what you get in the image are composable morphisms. And this is what is sometimes called the extended, well, almost extended symplectic category. I think this was considered by Weiss and other people. The point is that, well, this works just staying at the isotropic level. For some reason that I will explain tomorrow, or not today's, actually you want to make sure that these are not really just isotropic, but really Lagrangian. And that we'll see in a moment, or in a time, not in a moment, why this has to be Lagrangian, not just isotropic. Like in the example of mechanics, right, you saw that this is really Lagrangian. And well, you want to impose this in the general case. It's not a theorem, it's a condition of the field theory that the isotropic relation constructed this way must be Lagrangian. Okay. On the other hand, space theory is a bit more, because you do not work only on cylinders. You have more general situation, like several boundary component, and you actually decide what is. I mean, unless you have a time orientation, you decide what is incoming boundary and outgoing boundary and so on. So somehow you have to extend this to something like multi-category and so on. So these are somewhat easier to explain things. Okay, so next time we'll quickly finish this part and tell you why you want this to be Lagrangian, not just isotropic. And one thing that we'll see that there is a difference between the degenerate and non-degenerate theory, in the sense that in non-degenerate theory, when you project these relations to one of the two factors, you get the whole factor. So these turns out to be essentially these Lagrangian relation turns out to be graphs. So this is what happens in non-degenerate theory. There is no theorem that tells you that these relations should be graphs of mappings. So, and that's actually where things becomes interesting. That's what happens in the degenerate theory. And so this will give rise to the construction of these coisotropic submanifolds and the introduction that we study them homologically.